So I'm Mark Gelfo. I'm a principal with TLC Engineering for Architecture. We're a MEP and commissioning firm based in Florida, do work all over the Southeast. I've been doing designing and commissioning and testing various parts of hospitals and healthcare facilities for my entire career pretty much. And one of my favorite things to do is to commission emergency power systems in hospitals. So that's what we're going to talk about today, if that's okay with y'all. I apologize in advance. The handouts that you are going to see will bear some resemblance to what you see here. I was tweaking the presentation, we'll call it tweaking, until a few minutes ago. So, title of the presentation is With Great Emergency Power Comes Great Responsibility. Does anybody have any guesses as to what kind of theme I might have embedded in this presentation? Oh, Spider-Man. I'm a nerd, so I apologize in advance. If you like comic books and Spider-Man, you will enjoy this presentation. If not, well, that's your loss. I feel like this picture a lot of the times as a commissioning agent, literally holding everything together on the project. So I got a lot of stuff to cover, so I'm going to go through, scroll through this stuff. We'll talk about the course description and the other learning objectives. But let me ask you guys, how many people are commissioning authorities or do some type of testing, commissioning as part of their job? A few, okay. So when I normally do this presentation, I talk about the nuts and bolts of commissioning, a lot more depending on the audience, so I won't cover that kind of stuff. How many of you are electrical engineers, commissioning people, have electrical background primarily? Okay, that's more like what I expected. So presentation, except for a couple parts, isn't going to be as technical as you might think. So as commissioning agents, I think of us as commissioning superheroes. That's why I like to present this theme. So, like all superheroes, our job is to help prevent disaster before it occurs. And in the case of hospital emergency power systems, I like to think we're saving lives too. So maybe I'm a little full of myself though. So I'd like to start with a little bit of, get everybody on the same page with a lot of the nomenclature. A question already? Yes? Oh, no, you just need a handout? Ed, that man needs a handout. Peter Parker is Spider-Man, if that was your question. Terminology we use. We're going to talk a lot about the generators and why we call them engine generators, and the switchgear, paralleling switchgear or main switchgear. That makes up what we call the emergency power supply, or EPS. That's what's supplying the emergency power. You throw in the automatic transfer switches, and that makes up the emergency power supply system. And those are terms designated by the various codes. And the transfer switches are what separate our power into the various branches that we serve in the hospitals, pretty much as outlined by the National Electric Code 517, the life safety branch, which is what you think it is. It's life safety lights and things that are absolutely critical to life safety operations. And we have a critical branch, and then the equipment branch, which is also what you might think it is. It's the equipment in the hospital, air handlers, chillers, motors, things like that. And the critical branch is, I like to think of it as mostly focused on the patient care, the emergency power and lighting that is essential for critical care operations. That makes up our, along with the generator and any switchgear, makes up our EPSS. Then of course there's everything else, the normal branch or the non-essential branch. Sometimes we actually put some of that stuff on emergency power, even if it's not required. We might call that non-essential. The traditional jargon is just to refer to the generator as a generator or generators. Technically, it's an engine generator because it's made up of two main parts, a diesel or gas-driven engine, not unlike the engine in your car, although it's typically a lot bigger, that's converting the fuel into mechanical energy, and then we take that mechanical energy, turn it into electric energy through the AC generator. So we call it an engine generator because those are the main two parts. And then there's all the accessories that go along with it, everything from the batteries and the chargers and fuel systems and filters and mufflers and control panels, all those other pieces and parts, all of which have to be tested to make sure that the whole thing is going to work right together. Then on the fuel side, we'll have usually a main fuel tank, whether it's above ground or underground, that then feeds smaller day tanks, usually closer to the generator or at the generator, that usually hold about 3 hours worth of fuel, and then from there, fuel goes to the generator. You see a lot of exterior generators in their weatherproof enclosures with a belly tank or a skid-mounted tank that's right under the generator. That's the same thing as a main tank. You don't usually need a day tank because it's right there. But we're going to talk a lot about fuel systems, probably more than you want to. And then automatic transfer switches are where all the fun happens. This is where the switch that actually physically switches between the normal power, the utility power, and emergency power. So you got normal power coming in, emergency power coming in, and then the load going out. And that's what it looks like on the inside. You'll see some more pictures, and then are represented by this very clever diagram there. So why are we talking about all this? Well, hospitals use a lot of power, use a lot of energy, and most of that power is electricity. Yes, there's natural gas and some other sources, but most of it is electricity. And in most hospitals, the majority of that electricity is backed up by the emergency generation and the emergency power system. So it might be a good idea if we made sure that that stuff was working correctly. Because back when I started my career a long time ago, seems like there wasn't as much stuff that we put on emergency power. It seemed to be a lot closer to code minimum. And today, everything, including the kitchen sink, gets put on emergency power, which isn't always a bad thing. And based on some statistics in our own projects, you can have the emergency power take anywhere from about 5% to from 95% to 60% of the overall power. And the little pie chart shows how that breaks down, the blue being the normal on some averages. Equipment branch is typically the biggest branch. We always think life safety is the big deal, and it is, it's important, but the life safety branch is usually the smallest piece of it. The equipment, we always want to put air handlers and more chillers and more capacity on the equipment branch. So that's how that pie breaks down. I'm not going to cover this in too much detail because you all know about commissioning, but the question I get asked from owners, I'm sure you guys do too, a lot is, why do I need somebody else to come and test these systems? Don't I already get this? And I say no, you don't. Obviously, we know that the traditional process is unfortunately doesn't have the rigor in the testing. The EOR's scope traditionally doesn't have that level of testing and documentation that you would want, certainly in a life safety situation like a hospital emergency power systems. Sometimes it does, but sometimes it doesn't. And of course, our job as commissioning authorities is to ensure that we're trying to help the project and the owner transition from design to construction to occupancy, and that's where we bring the value. Now that conversation has been helped a lot lately since the IEC 2012 required some level of commissioning. At least people are more familiar with the term, even more so than they had been in the past. But as you all know, code requires HVAC in certain instances, lighting, hot water now, but doesn't say anything about emergency power systems. So it's important enough to test that the HVAC systems work right, but we don't have to make sure that the emergency power systems work right in a hospital. I need to talk to some people about that. So let's start by talking about what typically fails and why. And lots of stuff can fail. I'm going to talk about single points of failure, but the majority of the time it has something to do with the batteries or the fuel. It's not the actual engine generator itself usually. It's because the batteries weren't charged or it wasn't able to start, or the same thing with the fuel system. And that's usually because there was some lack of testing, lack of preventative maintenance. Maybe it wasn't set up right in the first place, or maybe we haven't considered single point of failure. And in my experience, there is almost always no matter how much redundancy you try to build into the system, there's almost always a single point of failure that is going to bring the whole thing down. You've got multiple generators and redundancy and paralleling gear, and then there's a single pump in the main tank of the fuel system that craps out, something like that. So we're always looking for those single points of failure, both in the design phase and then in the construction and acceptance testing phase as well. This is a list that I pulled off of from, I think it's Pure Power, 7 reasons why generators fail to start. You can see it's battery failure, insufficient coolant, fuel leaks, oil leaks, controls errors. My favorite, number 7 is my favorite. The fuel tank was empty. I mean, come on, guys. So if we set up the systems right and commission them right in the first place, and the facility does ongoing testing that's required, I'll talk about that a little bit at the end, that makes your systems a lot more reliable. You guys can stop me with questions anytime. Okay, that's the silence of understanding there. So I'm going to talk about what we do for testing emergency power systems in each of the phases, starting with the design phase. And so I'm not going to go through what we do is, what do the commissioning authorities actually do, because you guys know that. And what we do from the emergency power system side is exactly what you do on the HVAC side. We want to be involved in the job. We want to look at the documents. And this is where we can make a lot of difference, just like we can on the HVAC side. But unfortunately, we don't get brought in a lot of times until after that phase is complete. Now, just like on HVAC commissioning, sequences of operation are very important to us. But unlike them, and you might complain because the sequences that you see are not great, at least you get sequences of operation on your drawings or in your specs. If I'm reviewing a set of documents for emergency systems, I can almost write the first comment without even opening the set or the specs, and that's to provide a detailed sequence of operations and provide the time delay settings for the transfer switches, because nobody ever seems to bother to put that in the document. So that's a constant fight. And all we're looking for is something that starts with, upon loss of utility power, the following shall happen, right? And then that hopefully the design team has thought that through. Certainly, especially if there's bigger, more complex systems, multiple generators that get into load shedding schemes, and might be some real importance into how the transfer switches are programmed and what those time delay settings are, both for switching to emergency power and then switching back, because you probably don't want an entire hospital block loading onto the generators all at once. You might want to stagger that big pie chart of equipment load. You might want to do that in pieces. So that's all we're looking for, sequence of operations. Another thing I look for a lot of times in the construction documents is, have they thought through everything you're going to need on emergency power during an extended outage? And the word extended is the key there. Everybody can live with some minor inconvenience for a couple of hours in a utility blip. I live in Florida. We have hurricanes, so we plan for everything based on 5 days of no utility power. So the code requires, for instance, in kitchen operations, that you have to just have cold food storage, cold food prep, right? Well, after 5 days of eating cold bologna sandwiches, you're going to wish that you had put the rest of the kitchen equipment and had almost full kitchen operations on backup power as well. So those are the kinds of questions that we can get into and ask the owner, ask the design team. And of course, the single points of failure, make sure everything's testable, maintainable, so on and so forth. Now I've got a couple case studies of things that in each phase that I go through and that I've gone through. This one is one of the challenges that we run into all the times in hospitals is it's great when we build brand new greenfield hospitals, but that doesn't happen all the time. It's usually renovations. We're working in existing operating facilities that have to maintain power. So this is a project that I did where they wanted to replace literally all of the existing automatic transfer switches throughout the hospital. Well, you can't just shut them all down and take them out and then take your time putting them back new. By definition, these are very important loads that these transfer switches are serving. And one of the challenges that went with that is that all of the new transfer switches were going to be bypass isolation, which means that you can switch power and then rack out the actual switching mechanism and still keep it connected. But the point is that we're replacing really small stuff with really big stuff in most cases, and that's not always that easy. So we ended up having two different scenarios. So phasing and thinking through these things to minimize the downtime is really, really important. So we worked with the team to help think through those things, where if you have enough space, there's two scenarios. You can replace the transfer switch in the same place as the existing transfer switch. So it's not just a matter of ripping it out and putting in the new, because it takes about 8 hours to do all that and make that connection. You can't just have power down for 8 hours. So we've got to temporarily refeed the loads that are served from some other source, and come in and disconnect the emergency feeder and the normal feeder, pull out the transfer switch, put it in the new one, make those reconnections, and then reconnect the load, minimizing that downtime. So you have a couple of smaller, couple of minute outages rather than a whole 8-hour outage. Then the other scenario you have is where you can't physically put the new transfer switch in the same place as the existing. So what do? You got to find another place to put the new transfer switch. And generally, electrical rooms are very spacious and have plenty of extra room in them, so that's not usually true. So you got to find a place for it, and that's really the hardest part. But once you do, the phasing becomes easier, because you can put in the new transfer switch, make all your connections on the normal and the emergency side, and then the very last thing is run all your wire to the load, and then at the very last thing disconnect and reconnect. So the important thing is thinking through all these scenarios and a very detailed phasing plan. That was actually the easy part. Then it's the testing each one of these one at a time, because they're not going to do 5 of them at a time. They're going to do one at a time. So we're going to do one at a time, and then the next day they move and go and do the next one. And so we have to go in and test them to make sure that they're actually working right one at a time. So that was fun. Then we move into the construction phase. Just like on the HVAC side, we do the same things. So I like to show some pictures, what I call things I can't unsee, and because I like to take pictures when I go to construction sites and construction phase and acceptance phase, and some things are just really horrifying, like Venom, and some things are you just shake your head at, say I can't believe that, like 1970s TV Spider-Man. Right there. That's actually a TV show. He's standing on a ledge. It's not even, this is how I grew up. This has nothing to do with emergency power systems. I just like this picture because this is a job that I worked on, and clearly they've put the door in the wrong place. See, that's funny because the exit sign is over there. This is more realistic. I called before I got on the plane and said, "Are you ready for testing?" "Yes, we are ready for testing." And this is what I found when I got there. Clearly the control panel, clearly they were not ready for testing that day. And sometimes you can just tell just by walking in, if the project doesn't look ready, then it's not ready. This is not during construction. This was the day of the final H-day inspection. I like this one because this isn't during construction. This is before the project had started. This was a renovation project, and we were going and doing some investigation, and this was the existing that we found, which I guess is why they were renovating it. If you can't read that, well, I guess you can. This is like, do not stick your hand in the hole. This is a starter. So I'm a smart ass, so of course I, was going to put my hand in the hole. My favorite part is there's an arrow, as if you couldn't tell where the hole was, rather than actually just put a little piece of sheet metal over the hole. This is a door. I'm standing inside this new electric room in this renovation project, and this is one of the egress doors that is missing the hardware. And not only is it missing hardware, I mean, it's supposed to be egress hardware, panic bar, and it's drilled for the wrong hardware, and there's no hardware on it at all. And you think, okay, so what? It's a construction project. I took this picture during the final inspection with the AHJ when they were supposed to be getting their CO that day. So that was a comment. I stood in front of the door so they couldn't see it. I was joking, of course. This is more cooler in the hospital, and the lighting motion sensor, occupancy sensor right outside of it, I assume is some type of early warning system for the zombie apocalypse. It just cracked me up. I don't know how this water bottle got up in these pipes. I wrote it at least 2 times in 2 different field reports, and finally I gave up and I just got a ladder and I took it down myself. We test card access and door access, door control systems too, and these doors were not unlocking, they were not releasing upon fire alarm. When the fire alarm was activated, and the contractor said, it worked yesterday, that answer. So we went in and looked at it and like, well, there's no fire alarm wiring there, so I'm not surprised. So the engineers on this one, they did a great job in specifying these vertical louvers for the generator room to help prevent wind-driven rain from entering the generator room, keep the room dry. But somewhere in there they missed the details about what happens where the panels meet and where the panels meet the wall. There was nothing in the drawings or the architectural details. So once they were installed, there was a 1/4-inch gap between each of the panels and a bigger gap along the wall. And so I said, hey, how are we going to fill this? And we had to bring everybody together, and they had to figure it out, and they did seal it eventually. I'd like to think they would have figured that one out without me, but there's a lot of things that I'm going to talk about that would be so much easier if we got involved during the design phase, and I'm sure you guys see that all the time too. EPO switch, emergency power off switch for the generator is required to be outside the generator room. I'd like to think if I had reviewed the drawings during the design phase, I would have asked the question, hey, where's your EPO switch? Didn't have that, so when I got there during the construction phase, I said, hey, where's your EPO switch? And they said, oh, that's a good question. So they installed one after, but later than it needed to be, and it was, 3 RFIs and a whole thing. This is another, sometimes we can be helpful to the design team too, the engineers, when they don't get enough space in their, for electrical rooms. This is literally the biggest wireway I've ever seen in my life. It's 2,500 amps, and you've got the emergency power coming in from the generator, and then a big wireway, and then it goes out to the different branches there. And you think that was crazy, and it is, but it's because they couldn't get any electrical space to put a switchboard. The only space they could get carved out was this little, convince anybody to give them, was this little room that wouldn't even have been big enough to put a switchboard in, let alone have working clearances. So it's one of the things from a maintenance and operations standpoint we can help clarify. Rusty? Yep, you got critical, and you got, well, I can't see every which is which, but yep. Well, and why do you ask that question? You have to have separations in the wireway. Yes, that's another problem. I'm almost sure they did. We talked about it, and I don't want to go on record about that. Nice new generator room, and we didn't think about how the conduits go from the battery charger on the wall over to the batteries. I didn't think about it until they actually ran it across the floor. And we were talking about single points of failure. Oh, I wonder why my batteries aren't charging. It's because we literally kicked the wires loose, ran a big cart over it. Things like that you can't even think about. So thanks for indulging me. That's the only fun I have. That and superheroes. But the biggest thing I hear, the thing I hear the most often during, when I'm on construction sites and during acceptance testing is, that's not in my scope. Because just like in HVAC systems, there's lots of different pieces being provided by lots of different people. So you got the generator vendor, and you got paralleling switchgear manufacturer, and you got transfer switches. Come from a different vendor. Fuel system, the main tank's provided by one person. The day tanks might be provided by the generator people. They might be provided by somebody else. So you got the mechanical guys. If there's ventilation for the generator room, of course you've got plumbing subs and the electrical subs who's ultimately responsible, but doesn't hold any of the contracts, and then there's me. So I hear that they say it's not my scope, and I say I don't care, because that's my job is to make sure that we're bringing everybody together. And of course, there's always the photo finish, trying to get everything, the kickoff meeting, everybody's, yes, we're going to be done, and commissioning is going to be integrated into the blah, blah, blah. You've heard it all. Now, the difference that is our advantage with emergency power systems versus trying to get your control systems installed is that the AHJ is going to test the emergency power system. So they're not going to get the CO without that. If we could figure out a way that they can't get a CO without the control systems being, fully functional, that might be a thing. But at least we've got that going for us, that we're going to help them. And that's the way I look at the emergency power testing, is to try to help them get ready for the AHJ who's going to come and do their CO inspection. Because if it works right for me, chances are it's going to work right the next day when the AHJ comes. So there's a thing that I've been running into a lot lately on generators and grounding systems. And this is kind of a highly technical part that I'm going to go through really quickly. If you're really interested, I'll be happy to talk to you about it afterwards, but I don't want to sacrifice the testing part of the discussion for a seminar on grounding. But in this project, there were two generators. There was a generator, and then they were going to put another one in there, which is fine. That happens all the time. But when you're adding new generators and transfer switches to existing generators and transfer switches, it is very important that we make sure that the grounding systems are appropriate, and the transfer switch types, whether they're 3-pole or 4-pole, are appropriate for the type of grounding. Now, does anybody know what I'm talking about when I say 3-pole versus 4-pole transfer switches? One guy, yay, Rusty. And separately derived and non-separately derived grounding systems? It's a little technical, it's a little dense, and the one thing that I want you to take away from this is if you're near generators and have to, oversee their testing or talk to the guy who's doing their testing, is that this is a thing. Right, that with 3-pole transfer switch, with non-separately derived grounding systems, you need 3-pole transfer switches, and with 4-pole, or with separately derived grounding systems, you need 4-pole transfer switches. What does that mean? I will tell you very, very briefly. So there's 2 transfer switches, right? And they look exactly the same on the outside. You wouldn't know that one's a 4-pole versus a 3-pole and what that even means, but a 3-pole transfer switch, the one on your right there, is a switch. Remember, transfer switch is just switching. It's a big switch, and it is just switching the A, the B, and the C phases. These are 3-phase power systems, so it's just switching your phase conductors. Your neutral conductor is over here. It is not switched. The neutrals from the normal and the emergency and the load all come together on a common set of lugs. So that's why it's called a 3-pole switch. We're only switching 1, 2, 3 poles. 4-pole switch is where we're the same thing, but we're also switching the neutral. The neutral comes here, and it's also switched too. Why do we do that? Well, it has to do with how the systems are grounded. And the separately derived, we're always bonding the neutral and the ground at the utility service. So the real question is, do we bond them together at the generator, at the EPS service too? So if we do, then we've separately derived a ground at the generator. If we haven't, then it's not separately derived. See, I can even hear that it's complicated in my head as I say it, the words coming out of my mouth. when they're bonded, when we have a separately derived system, we bond the neutral and the ground together. So what you have here is the neutral, it's hard to see, but the neutral lugs come in here, there's ground lugs down there, and a bonding jumper that connects the two. That means they're separately derived. We've separately derived the grounding over here, over at the emergency side. Non-separately derived is when you do not have that connection. This was done incorrectly where they were bonded together, where there was a mix of 3-pole and 4-pole transfer switches, but they had 3-pole transfer switches existing. So there should not be, so it should be a non-separately derived system. So this is the technician actually removing the bonding jumper from the neutral bus that was connecting the ground bus. So again, if you don't remember anything else, try to remember 3-pole, non-separately derived grounding, 4-pole, separately derived grounding. And this is a really fancy chart I drew on the plane coming here because I couldn't find a graph that really represented what I wanted to show. And just real briefly, try to show, we're showing a sample of a 4-pole switch and a 3-pole switch. So what we're really just representing is what the neutral conductor. So in the 4-pole switch, it's switched, and in the 3-pole, it's not. This really has to do with getting ground fault protection to work properly. And we want, when there is a fault, we want the ground faults to flow where we want them to flow so that the ground fault protection can see all of the fault and actually trip the way it's supposed to. So in this separately derived system, see we've got the neutral and the ground bonded together here, so it's separately derived. So if we have a fault, the fault is going to go, we've switched on the emergency side, we've switched and it goes through this way, and there's only one path for the fault to take, and the ground fault protection sees it all, and life is good. If we had a 3-pole switch on this system, there's actually 2 paths for the fault to flow, because we're connected over here, so it can take this path back over here to the source. So the ground fault protection on this side that we want to either alarm or trip isn't seeing all the ground fault, and it might not work. This is the short version, believe me. In the other case, where we have a non-separately derived system, we don't have that bond here anymore. We want to have a 3-pole switch. This would be the right place to have a 3-pole switch, which if we had a fault here, then there's no there's no connection between these two, so that's good. So fault goes that way. If we had a 4-pole switch in that system, actually we have what's called a floating neutral, which can cause all kinds of problems on your system and overvoltages and other problems. So that's bad too. And it's a thing that I've been running into a lot on projects lately where it really comes down to not fully investigating what's there with in an existing hospital and having a mix and not knowing not thinking that through with the existing systems. You can't just come and slap on your new generator and your new transfer switches and hope everything works right. So I'm not even going to ask if you have questions about that. Come see me after. So we move into the acceptance phase. This is the fun stuff. This is what we want to talk about, right? So what do? We test stuff. So the same thing we do on the HVAC side. People ask me, well, how do you go about testing the systems? And I tell them that we start with NFPA 110. That is kind of the Bible for what we need to do for installation acceptance testing. It's not, well, that's how we base most of our tests, is making sure that we are complying with all of the requirements of NFPA 110 and basically write the test procedures around making sure that those requirements are met, of course with the OPR and the BOD as well. Another way to put it then is that we start small. We test each of the components. All those different system components that I've been talking about, we test them one at a time. We test the fuel systems, we test the main tank and the day tank pumps, and then we test the transfer switches, all the wiring, and then test each transfer switch individually. Usually we're making sure that they've all been programmed first. All that programming, when I said nobody has said what the time delays need to be set at, usually what happens is when I show up, the transfer switch technician is standing there and said, all right, how do you want me to program these time delays? I'm like, I could tell you, but I'm not the engineer of record. And so then that goes through several other gyrations, and Sometimes we have to say, all right, well, let's set them to this for now because I can't get the engineer on the phone and he hasn't answered my questions, and then we'll go from there. But they have to be programmed to something. Then we test the actual engine generator and all its components. I like to be there for the load bank testing, and hopefully the engineer has specified load bank testing because it really helps with all that. So if I can witness that, it checks all those boxes and all the different components, and it helps us to ensure that the generator can actually produce the capacity that it's rated for. And then my favorite part is we turn stuff off and we see what happens. This is more fun in a brand new facility where you can like literally just kill the main. But in existing hospitals, you can't just go turn this stuff off even in part. So we're usually testing one transfer switch at a time. Simulate normal power loss to that one transfer switch. Make sure it transfers, and everything else that's supposed to happen happens. Obviously, every project's different, and we write those tests to be meet the project requirements, obviously, but that's essentially what it is. We turn it off and see what happens. And functional tests are usually go through all that, and then and we test all of the alarm and annunciator points one by one for each generator. So it takes a while. I have learned more about fuel oil systems in my career as doing generator testing and stuff than I ever thought I would, because apparently nobody else ever thinks about these things. And the fuel systems are kind of important. So, yeah, you can see that. So one of the things that we want to look for, is that there's actually a fuel system diagram of some sort in the construction documents. Hopefully where we're doing a design review, that's one of the first places I'll look to see if we've got a diagram, because one of the most important things is to actually have a fuel system diagram that lays out all of these different pieces, parts, and components of the system. That there's an actual sequence of operations. What happens when the generator starts? When are these pumps? There's day tank pumps and main pumps. When are they supposed to turn on? When are they supposed to turn off? Has anybody really thought that through? I said pumps. Have we thought about future generators and whether there's provisions to extend that piping in the future? The main tanks, other parts of the system, how are we filling the system? How does that work? The alarm systems, and then valves. Do we have the right valves in the right places? And sometimes even when we get a diagram like this, you can tell pretty quickly that when it's just a generic detail that's been slapped on the drawings. But that's all we're looking for, is to make sure that somebody has thought through how these systems are going to work. Because this example, in this particular case, this is a day tank. Happens to be outside. That's not the important part. One of the requirements is for there to be a hand pump at the day tank, so that you can, if the electric pump doesn't work, you can manually pump fuel. First thing I said when I got there was, hey, there's no day tank. Is there supposed to, or no hand pump? Is there supposed to be a hand pump? Everybody looked at me like I had two heads, like they had never heard of such a thing before. So there was no diagrams on the drawings, no details. The plumbing guy who was handed this day tank and said, install this, didn't know what to do. So he just guessed. He just took a guess and he put in, a hand pump, and he was all proud of himself that he figured out how to pipe it in there, because I said, hey, you should talk to the engineer and get a detail from them. He just piped it in, but he piped it just in line with the supply piping. And when I went to test it, I couldn't even move the thing. There was just so much back pressure on it. I said, I don't think that's good. I said I didn't think it was going to work, but this is what they ended up doing, which is kind of what I suggested in the first place, but check with the engineer. There's usually a bypass and then a separate line for the hand pump. But my point is that these things are not that hard, and we make them hard. Or we make them hard by not having thought through them during the design. Another one I see all the time is, a day tank has, or a main fuel tank can have multiple levels of alarms, low fuel, pre-alarm, low fuel alarm. Same on the high side, high fuel, pre-alarm, and alarms. And what level should those be set at? This is a question I get all the time, and my answer is whatever the EOR says they should be set at. And that's a whole different, thing. Exactly. Just making sure they get set and tested. So we got to test. We got to pump fuel out to try to get to that low level, and then we got to pump fuel in to try to get to that high level, and hopefully fuel doesn't spill all over the place, so because that happens too. And then testing the different pumps and things like that. So running along. Then we move into the post-occupancy phase. Just like in commissioning of HVAC systems, we do the same things. And of course, it's important to involve the owner in all of this stuff, all of this testing. And what I found is you got to clarify who the owner is, because I'm sure you guys have had this too, where you have a person who's shadowing you or sitting in the meetings, and then that person is not the person who's actually responsible for operating and maintaining systems. That's the guy you want. That's the one that is going to actually be responsible for keeping these systems up. That's the guy you want to be involved in this whole process. As in this project, the gentleman who was the maintenance man who was going to taking care of the systems, he told me exactly what he wanted the transfer switch time delays to be. I'm like, all right, we'll take that. The owner said what he knew exactly what his existing ones were and why, and so we went with that. The engineer had never bothered to ask him, so at least somebody did. And then sometimes we try to help out with, NFPA 110 also talks about all of the ongoing weekly, monthly, yearly testing that is required for generators and transfer switches, and so we try to help facilities with that because they've got to operate the stuff. So if they're not already familiar, we've in the past set up. We've set up guides for them right out of NFPA 110. And then my last case study is something that seem to run into a lot, is dealing with controls and harmonics and other electronic equipment, because even though the transfer switches transfer pretty quickly, in the blink of an eye, what happens when they switch? We still lose power for a second. And that happens when they transfer from normal to emergency. It also happens when they transfer from emergency back to normal. And one of the things that we find is that there's a lot of times controls failures because things, didn't have UPS backups or lost their programming or just got confused when they switch back and forth for power. So that we end up causing problems to the HVAC guys a lot of times because we've switched power back and forth, and things that we didn't know were going to failed. So that's why we do that integrated systems testing. Because
a couple of projects recently, a big issue with the owner where you found that he got open transition ATS closed, but now he found every time he does his monthly test, he's losing the equipment. That's not something likely to happen. That's one case they ripped out the open transition replacement closed at a pretty big cost.
Oh, sorry, did you guys hear that? The comment was about open transition transfer switches versus closed transition transfer switches. And I didn't get into that level of detail, but closed transition basically connects the two sources before it switches. So there theoretically is either a much, much smaller or no interruption of power. But that's more expensive too. And there's other issues that can come along with that. So that's an important conversation to have and make sure that the owner knows what they're getting and why. The question is if we've seen whether owners, hospitals are going towards open transition or closed transition. My experience has been that actually most hospitals have open transition switches, don't have that overlap because they generally can tolerate the couple of cycles of interruption. There's not, short of problems with control systems, it's not super critical like in data centers. Data centers are always going to want to have closed transition, so there's literally no interruption of power, even with UPSs. And so, yeah, I somewhat closed transition, but most of mine have been open.
Or delay transition on equipment branches. Because
Right.
sometimes that open transition, it'll try to sync up and be in phase, but it's still pretty ugly.
Right. So
A
the
lot of sensitive electronics uses a flow. It's a delay transition for a few seconds.
we do that. We see that all the time on equipment branch where there's actually a delay. We purposefully delay there's actually a center position, a center off position. So it's programmed where it goes from normal to this center off where it's not connected to anything for some specified period of time. The code doesn't say it has to transfer within 10 seconds. Your life safety and your critical has to transfer within 10 seconds, but your equipment can take as long as you want. So you switch it to that center off position for however long you want, and then you switch to the emergency. So there's no reason to do a closed transition in that period because you're purposefully trying to have a delay. The other thing that I've run into, and it's kind of weird, is harmonic issues and big VFDs producing harmonics. I've had a couple of projects where big chiller VFDs have had harmonic issues, even with, well, I've seen it in both cases where it didn't have the right harmonic filtering or that wasn't addressed, but I've seen it where the VFDs did have some harmonic filtering too, but this chart is supposed to show, and one project in particular that I'm thinking of where these are the harmonic values without filtering and these are with it, and you can see the 5th and 7th harmonics have some big numbers there. So this is what we had. If you remember from your high school physics class, this is what a typical voltage sine wave should look like, nice and clean. It doesn't really look like that in reality, but when we have big harmonic distortion, you get all these little waves in between. This happens to be representing the 5th and 7th harmonics that's going on with those chiller VFDs, and the resultant curve looks something like that, and those nasty little dips in there really cause havoc on sensitive electronics, different controllers. We found that these little UPSs that were backing up many, many things throughout this hospital all went crazy every time we switched from emergency power back to normal power because it was producing those harmonics were on the system. Well, I guess not when it was switching, but when it was on emergency power, those harmonics being produced by those chiller VFDs were just driving it nuts. And it's something we didn't see when they were on normal power, just when they were on emergency power. So it took some time to track down. So it's something to look for. And that's really it. Just a reminder that it takes a whole team of people to make these emergency power systems work right, to make sure that ensure the safety of the patients and staff and visitors, just like the Avengers. Way in the back, question.
Just add one thing to your presentation. So private functional testing, the one thing that we have found a lot, maybe probably 80%, is that the breakage both on the normal side of the transfer switch and the generator are not set for the coordination study.
That's an excellent one. How did I miss that? So the question, if you didn't hear it, is that the breaker settings on the normal side and the emergency side of the transfer switches are not set properly, and that's very important for selective overcurrent protection. And yes, that's a thing. We certainly need to make sure that that's caught too. Or yeah, if there's even a coordination study done. I'm a little spoiled. In Florida, it's actually required by code to submit the coordination study with the design documents. So it's required to be, for hospitals, it's required to be done, so that's at least half the battle. Other states I work in, they look at me, again, like I've got multiple heads, coordination study, the vendor's gonna do that. Okay, well, we'll see about that, and then making sure that they're actually set right. Very good point, thank you, sir. I love this time slot right at the end of the day. I'm the only thing holding you up from dinner in the bar. No questions? Really? I'm surprised. Yes, sir.
I was just wondering if you've ever encountered switchgear at higher altitudes not actually fail. I was surprised that switchgear over 11,000 feet
So the question was if, let me repeat the question first and then you can keep going. Was about whether we've had problems with switchgear not being rated for high altitudes. I'm from Florida, so high altitude is like 25 feet. We worry about keeping it above water. And I think you said you had, what, 11,000 feet and the switchgear failed? Well, I literally have not experienced that, but I haven't worked in high altitudes either. The switchgear wasn't rated for that high of an altitude. In the specs that I go through, there's always an altitude rating that I just skip right past that, because it doesn't apply for most of the areas that I work. I'd be interested to hear more about that afterwards. Other questions?
How typical is it that you test loss of phase? Is that something that's usually done on every project?
Testing loss of phase. We don't typically test that specifically. So I guess that's the answer to your question. No, we don't test that. I don't know what I was going to say. I've seen it happen as part of the. Sometimes that gets ferreted out during all the testing, especially the load bank testing. A lot of times you see the rotation. Instead of it being ABC, something's been wired, CBA or something, and that gets uncovered during the testing. But we don't typically test different fault. Pull that wire out, see what happens. We don't typically test for those types of things. Right, sir.
ASHI, the American Society of Hospital Engineers,
Sure.
has a emergency generator testing nomograph, I think they call it. It's just basically a guide. Are you using anything like that when you're developing your procedure? I mean, like a checklist of we got to test this, all the things that need to be tested?
Yes, is the short answer to that. There's also the health facility commissioning guidelines that ASHI's put out that we reference for overall what should you commission in a hospital. I'm a big fan of that document because they want to test everything under the sun. I haven't referred to it in a while, but inherently we're trying to test to all those things, or at least ask those questions to make sure that somebody is telling us, no, we don't want to pay you for that. Sir?
This is not a hospital-specific question, but just a generator question. So oftentimes, the generators, your success, the short question is, do you have issues with getting verified success criteria for transient testing? Because what I see happening is, in factory, you establish a baseline success criteria, but it's based on a 0.8 power factor. Usually test the factory, test the generator, maybe do. But most owners buy a system-only load bank, which is more difficult for a generator to handle when it's tuned to the 0.8 power factor.
Mm-hmm.
And therefore, you're less scratching your head to do the math. This is something that runs into quite a bit because there's really no solution to it. It requires them to do test the testing in the factory as well. Or do you bring in a system reactive load to the site? You add a lot more money, and the owner doesn't want to do it, it's a lot of load bank testing.
Right. I don't even remember what the first part of that question was, but it was about transient testing criteria, and then about the load banks that we typically see. The answer to that part is no. I don't typically see enough criteria specified or described. It should be. And then as far as the factory testing, I try to suggest that the testing be done with a reactive and resistive load bank. Nobody ever does that, though. It's almost always 100% resistive load bank. I will insist, or well, I try to insist, if they, take my suggestions that we do a field load bank test instead of just a factory load bank. You can do factory load bank test, that's fine. I assume that somebody's going to do that, but I want to see it in the field. I don't want to rely on just a factory test. I want to see the field test because it helps with our testing. But typically that's going to be just a resistive load bank because that's what they have. Oh, I'll have to add a whole bunch of cost to the job to ship that in from California, I don't know, wherever. All right. I'll take one more question and let you guys go drink.
Let's come up with the identifications for these people on the street right now.
You have no idea how long I spend on this kind of stuff. It's ridiculous. And I changed it like 3 times. Clearly, Spider-Man's leading the team. Iron Man has to be the engineer, right? That just makes sense. And then, the owner, see, I actually think about this stuff. The owner is actually the only one who has the hammer to make people do stuff. I just go through and tell people, you should do this, and hopefully the owner agrees with me. The contractor holds all the contracts, but, there's a little bit of thought into it. Like I said, nerd. All right, thank you, everybody. I'll hang around if you have any questions.